Direct addition and conjugate addition of alpha-beta unsaturated aldehydes and ketones. What is an alpha-beta unsaturated carbonyl compound? Here is a general representation for the alpha-beta unsaturated carbonyl compound. Let's say that this is our carbonyl group, okay, and this carbon, which is adjacent to the carbonyl group, is an alpha carbon, and the next carbon is a beta carbon. So now between the alpha and the beta carbons, we do have a double bond, and therefore it is called as alpha-beta unsaturated carbonyl compound. Now, one important thing to say about this alpha-beta unsaturated carbonyl compound is that it has got two electrophilic sites. The carbonyl carbon, okay, this is one of the electrophilic sites, and the other one is the beta carbon. So these are the two electrophilic sites. We already know that this carbon is electrophilic, but how come this would be an electrophilic site? For that, we have to draw the other resonance contributor, because you can see that these two bonds, these two double bonds are conjugated, and therefore the electrons from this double bond can hop into here to form the double bond, and these electrons can be kicked onto oxygen. So let's draw the resonance contributor. So when that happens, it's going to put a positive charge on this carbon, which is going to lose the pi bond. And there will be a double bond between the alpha carbon and the carbonyl carbon. And this oxygen will have extra lone pairs of electrons on it and will have a negative charge on it. So this is the other resonance contributor. Now you can see that this carbon has got a positive charge on it. Now, because they have got two electrophilic sites, there can be two different types of addition. So one is the direct addition, and the other one is the conjugate addition. The direct addition is also called as 1,2 addition, and the conjugate addition is also called as 1,4 addition. Let's now look into the difference between direct addition and conjugate addition. In direct addition, the nucleophile is going to directly go and attack the carbonyl carbon and thrust these electrons onto oxygen. This is what we have been seeing in most of the reactions in aldehydes and ketones, where this nucleophile will go and attack this carbonyl carbon, thrust these electrons onto oxygen, and forms in tetrahedral intermediate, right? So let's draw this tetrahedral intermediate. And now once the tetrahedral intermediate is formed, we know that it is unstable. But if Y is strongly basic, then it's not going to leave from the tetrahedral intermediate. Instead, the O- is going to get protonated. So this is what we'll be getting as a product. Here, we needed to find out where these two groups are getting added. So basically, the nucleophile and the hydrogen is getting added to the carbon-oxygen double bond. Okay, let's say we give a number for carbon 1. This number has got nothing to do with the nomenclature. And this next position would be 2. So the two groups, the Y and the hydrogen, is getting added to the 1 and 2 positions respectively. So therefore, this is also called as 1,2 addition. Let's take a look into conjugate addition and see how it is different from direct addition. Now, in conjugate addition, the nucleophile is going to go attack the other electrophilic site, basically the beta carbon. So this is going to go and attack here. So the nucleophile will go and attack here. That's going to push the electrons onto this carbon. Now we can draw the resonance contributor for this structure, where these electrons are going to hop in here, and the double bond will be, the pi bond will break and it will move towards the oxygen as lone pair of electrons. Here are the two resonance contributors, and you can see that there is a negative charge on oxygen. Now this oxygen will be protonated. Once protonated, here is the product that is obtained, and this product here is an enol, because you do have a double bond which is going to correspond to ene, and you have an hydroxy group which is going to be an ol, and therefore this is going to be an enol. Now let's identify where the two groups, basically the nucleophile and the hydrogen, is getting added. So the nucleophile is getting added to the beta carbon, and the hydrogen is getting added to oxygen. Now let's give the numbering for the two atoms where the addition is taking place. So let's say that this is going to be 1. This carbon, this beta carbon, is 1. And this would be 2. You're trying to reach the other atom, 3, and then 4. Because the two species are getting added in the first and the fourth position, it's called as 1,4 addition. So this is the 1,4 addition product. And this enol is not a stable compound, and therefore it is going to get tautomerized to give the ketone. And during tautomerization, the pi bond and the hydrogen are going to change their, or they are going to switch their places, and therefore we'll be getting a ketone. You can take a look into the ketoenol tautomerism to see how this is happening. So this is the ketone.